So the idea of equivalences, we first talked about a few lectures back when we were talking in the context of conjunctions and disjunctions, ands and ors, also applies to these new logical operators, to conditional and biconditional statements. So what we're going to do in this lecture is look at some equivalences and use these to kind of get an idea of how those two operators relate to each other. So first, in the last lecture, we talked about these different forms of a conditional statement. We have the conditional, the converse, the inverse, and the contrapositive. What I want to do here is I want to answer just kind of a very mathematical question. Which of these statements are equivalent to each other? All right, we're going to do this using truth tables. You see I've set this table up so we can go through a truth table for all four of these. Now I'm going to kind of knock this out here. It shouldn't be too tedious. So we're going to do our usual starting point. Right, we're going to start with all the possible combinations for P and Q. We already know what a conditional statement looks like. A conditional statement looks like true, false, true, and true. Okay, so now for the other three, I'm actually going to write it right in the individual columns. So if I put the Q values here, the Q values, and the P values here, and what goes in the middle? Well, the way I remember the conditional statement is T implies F is always false, and all the others are true. So T implies F is this row, and all the others are true. So already we can see, right, that the converse and the conditional, and the original conditional, aren't equivalent to each other. All right, so now let's try the inverse. This is going to be not P, that's false, false, true, and true, and not Q, which is false, true, false, and true. And then we apply the same rule, right? The only T then F is this one here. So this is false. All the others are true. So we're seeing now we got a positive result, right? The converse and the inverse are equivalent. So let me write that down here because I start summarizing our results. Q implies P is equivalent to not P implies not Q. And then we've got one more to do. So this one is going to be the contrapositive. False, true, false, true, false, false, true, true. And again, I have only one T then F. That's this one here. And the others are all true. And this one does match the original conditional statement. So a conditional statement is equivalent to its contrapositive. Every once in a while, that will come in handy, right? Sometimes you'll have this statement and you're trying to prove it and you're kind of stuck, right? Well, if you rewrite that as the contrapositive in that contrapositive form, and then try to prove that instead, every once in a while you'll come across a situation where for some reason that statement is easier to work with, and because that statement is equivalent to your original conditional, proving one is the same as proving the other. So you see now here we have kind of a practical example of this idea of statements being equivalent, right? If we prove one version, we've also proven the other. All right, so conditionals versus biconditionals. How do these things relate to each other, right? Well, I have a biconditional here, and I'm not going to actually prove this equivalence. If you want to, I encourage you to go ahead and create a truth table for the right-hand side and compare that to the biconditional table. And you'll see they do come out the same, but I won't make you sit through watching me do another truth table. Notice what this is saying on the right-hand side. A biconditional is equivalent to a conditional and its converse. All right? In other words, for the biconditional to be valid, both the conditional and converse has to be valid. And again, and we're going to see more of this as we get into the later chapters when we start actually thinking about proving things. This tells us what we have to do to prove a biconditional statement, right? A proof of a biconditional, of an if and only if, actually requires you to do two proofs. First, you have to prove that the conditional version is true, and then you have to prove that the converse is true. Both of those have to be true in order for the original biconditional to be true. So that's kind of the relationship between the two, right? How a conditional and a biconditional kind of connect. All right, so what's next? We're going to keep talking about these conditionals and biconditionals. Specifically, we're going to talk about conditional statements, because the one thing we still really would like to do is talk about what is the inverse of a conditional statement. That'll take us one step closer to a complete set, right? Because we've already seen in previous lectures what the negation of a negation is, what the negation of an and is, and we've seen the negation of an or, right? This is the double negative property, and these two are De Morgan's laws. So in the next lecture, we're going to add to our list, we're going to talk about what the negation of a conditional statement is.